welcome. One of the things I worried about when I began this was the visual aspects. When I did this in a lecture hall, I had slides and later on some electron, illustrative aspects to provide you with the proper knowledge of what I was talking about. And I thought maybe this would be close to impossible for me. But come to find out, it's actually much easier than I anticipated. So today you get to indulge in my great lacking, which I mentioned earlier in the course, and that, of course, is a type of artistry. Today we're going to start covalent bonding and the orbitals related to them. Now, Alpha, I mentioned earlier, AUF, BAU, he stated in his principle that electrons will fill all the suborbitals in consecutive order. In other words, the S will fill before the first of the P, and the D will, or the P will fill before the D, and so on. Now that comes up to conjecture when we start talking about hybridization. Today I'm going to roughly go through hybridization because you need to have at least a working knowledge of it. If you want any great depth, it's available. You can go out and check online. The drawings will be better. But today let's talk about it. Now, if you notice the repetition, I've used the same compounds over and over again because I want to get at least a great in-depth study of a few compounds. The first we'll start out with is the sp3 hybridization. And what that does is that it allows the the 2p, in the case of methane, CH4, to share electrons, carbon with hydrogen. And if you'll notice that the carbon, which has 6 electrons incidentally, the 1s and the 2s are full. 1s is completely removed from this scenario, and then the 2s is filled first with the 2 extra electrons, carbon being 6, move into the px and the py suborbitals. In the case of sp3, the remaining 3 slots to fill up to the second shell are provided in blue by the hydrogen. And hopefully that's clear. I decided to throw in another one, ammonia. Now, ammonia is quite similar, except that it has an extra electron more than carbon does, and for nitrogen, and thus you have the 1s full, the 2s is full, and the XYZ each have 1 electron in it, with the hydrogen providing in blue the extra electron for each. Next we go into something a tad bit more technical, and that is with ethylene, the sp3 hybridization is followed by the sp2 hybridization in this instance. Now, I tried to draw it out, showing the sharing that exists in the sp2, which it contains 4 suborbitals. I think I've fairly well covered it. notice that each of these little dumbbells or look like prolonged circles are actually orbitals. And the double orbital, the sp2s in the center, show the double bond between the two carbons. And the rest of them show the hybridized bonding that completes the sp2s. It's, again, all this is reasonably straightforward. I'll get into greater detail as we go on. So now we have sp3 with methane and ammonia, sp2 with C2H4, and sp is for carbon dioxide. Now, down into the, remember everything's patterns when you get into complexities. Now you can readily understand you can't see any of this stuff, so you have to illustrate it with diagrams and models. Now the rules here are 4 groups for the first one, and they're 1, 2, 3, 4. SP, let's see. Looks like I took out the, there we go. That makes sense. We got an SP1 and a P2 and a P3. And you add them together, it becomes an SP3. Now the angle for this is 109.5 and is said to be a tetrahedron. The next one is has 3 groups, SP1, SP1, which adds up to be SP2. And its angle is 120 degrees and it's trigonal planar. And group 2 groups, the next one, 1 and 2, and that's SP1, which is SP, which is 180 degrees and is linear. Now what I've done with that is go through and draw this out and then add a few at the end here. We'll try and separate them so they're not inordinately confusing here. Remember I said the 2 group, which is SP, is linear, and SP is indicated here as 180 degrees or linear. With the 3rd group, the 3 groups, and the reason it's grouped like that, it means the number of effective pairs for bonding. That's what it means by the groups. So 3 is a trigonal planar, SP2, and your angle in the reference frame is 120 degrees. And then the 4, which was the one that we started with, was tetrahedron, is SP3 for the same reason it was SP3 up there and up there. And your angle is 109.5 degrees. Caused by the 3-dimensional aspects of it. It's not a single plane, but it's 3-dimensional. Now there's others, and I don't get into very many of them, but I'll hit a couple of them. The DSP3 is for something like phosphorus pentachloride, and what you have is a linear frame straight up and down, and then a reference frame at an angle and one perpendicular here. And it's called trigonal bipyramidal as far as the structure. And it has a 90-degree angle for one of the frames and 120 for the other. And it's called a DSP3, using the D shell, the S, and the P shell for the shared electrons that allow the covalency to occur. Obviously, people don't carry around phosphorus pentachloride very much. It's probably fairly expensive. And the last one I'm going to bother you with is D2sp3. It's an octahedral, octahedron, and it's shown up here as sulfur hexafluoride. And now you got three reference frames, two here, and then one at a 90 degrees, three-dimensional in and out. And this one in the three-dimensional coming out is a 90-degree, and that one and the two-dimensional in frame is 90 degrees. So you have your 90-degree angles for your D2sp3, which is an octahedral structure. Trigonal bipyramidal. Again, the reason, of course, is the trigonal here and the bipyramidal is there, which should be reasonably understandable. 90 degrees and 120 degrees. And if you wish to delve into this deeper, I mean, some textbooks have whole chapters on this. For a survey course, I just can't rationalize spending like 5 or 6 small lectures on this. This gives you an introduction if you want more depth, or the course that you're taking in the actual college or university, or even AP chemistry in high school. And some courses are difficult enough that they actually cover this in high school. I recommend that you go online, find out a structure that you want, and then walk through it. They have reasonably good explanations. Sometimes they get lost in the weeds because they start talking about derivations of certain frequencies or derivations of certain suborbitals, energy, and that kind of stuff. And it's just not practical for a survey course. So hopefully this gives you an idea of covalent bonding orbitals. The one you're most familiar with, of course, is the sp3 hybridization, which is methane and ammonium. And it's also the same one that's water. Water is sp3 at 109.5 degrees for the angle. So you got that one as the predominant. You get some sp2s that you deal with, but the SPs, of course, are quite common. It's a linear double bond, triple bond between the two central atoms. So that's not unusual. But when you're delving into DSP3 and D2sp3, it's more exclusive, if you wish, and more unusual. I hope this gives you a little bit of an idea of what we're talking about.